So before starting, I would like to take a moment to honor and remember my dear supervisor, Dr. Laurent Delannoy, who sadly passed away on May 12. Laurent was an exceptional researcher and scientist. He was also a mentor and friend for all of us. His dedication and kindness left a high mark on our team and our work, and especially in this paper. I just want to say to Laurent that he will be deeply missed and his spirit will always be a part of all of us. So, good morning. First of all, I would like to thank Prototype Society for giving us this opportunity today to present our recent published paper in ChemCat Journal, which discuss the atomic scale observation of the structural dynamics of supported gold nanocatalysts under butadiene by in situ environmental transmission electron microscopy. So this work was carried out during my PhD thesis 2 years ago under the direction of Dr. Jason Nelaya in the Material and Quantum Phenomena Laboratory at Université Paris Cité, of course in collaboration with different experts of the field at LRS and ICGM laboratory in France. So why are we interested by studying selective hydrogenation of butadiene reaction? As it's known, unsaturated hydrocarbons and especially light alkenes like butene, for example, are used as reactants for polymer synthesis in industry. However, the production of light alkenes by cracking of petroleum hydrocarbons can produce a lot of impurities like butadiene, which is able in low proportion to poison the catalysts used for polymer synthesis. That's why our aim was to use the selective hydrogenation reaction as a purification process to selectively transform the butadiene impurities into butene and then to obtain high purity alkene stream for polymer industry. So what about the reactivity of gold nanocatalysts during this reaction? We study in collaboration with Dr. Laurent Delannoy and Dr. Catherine Luis at Sorbonne University the catalytic performances of TiO₂-supported gold nanoparticle between 30 and 300 degrees Celsius. So the results show a high catalytic performances of gold nanocatalysts, showing on a side full activity of gold nanoparticle between 200 and 250 degrees Celsius with full selectivity to butenes. The question is, how will this gold nanocatalysts work in real condition? So generally, the hydrogenation of butadiene to butene require two processes: butadiene adsorption and hydrogen dissociation on gold nanoparticle. However, the nature of gold nanocatalysts' active sites during these two processes is under intense debate due to the lack of direct observation of this gold nanoparticle in the reaction environment and in real conditions. That's why our aim was to identify the nature of these gold active sites in selective hydrogenation reaction by studying the structural dynamics of gold nanoparticle by atomic scale in situ and operando environmental transmission electron microscopy in real catalytic condition. So the objective was first to study in situ the structural dynamics of gold nanoparticles separately under hydrogen and then under butadiene, which is the subject of the paper, and then to study in operando condition the structural dynamics of gold nanoparticle and the reactive mixture of hydrogen and butadiene. So of course, to achieve all this study, we need the good setup. That's why all our environmental transmission electron microscopy studies have been done using the Super TEM GEOL ARM 200F, having a double aberration corrector of the objective of the objective and the condenser lens. So to study or to monitor the catalysts during gas phase experiment, we use a prototype atmosphere gas holder dedicated to the study of catalyst in gas environment and having a high pressure gas cell. So this cell made by prototypes allow us to heat the catalysts up to 1200 degrees Celsius and the inlet of the holder can be coupled to a manual gas distributor, which allow us to introduce the gas to the cell up to atmospheric pressure and then to obtain the real catalytic condition. Also, to achieve operando condition, the outlet of the holder, we coupled the outlet of the holder to a residual gas analyzer having a mass spectrometer, which allow us to calculate the composition of the reactant and product gas. So despite the different limitation of this homemade couplet setup, we success to overcome all the limitation and to keep the atomic resolution of the super TM in complex, operando, and in situ condition. So before starting to discuss the results in the paper, I would like to discuss some previous results already published in small journal in 2021. We're discussing the reactivity of gold nanoparticle under hydrogen. So as we see here, the figure shows the reactivity of two gold nanoparticles having a size of 5 nanometer and 3 nanometer initially under argon, and then when exposed to hydrogen between 400 degrees Celsius and room temperature. So as we see, the larger particle keep its initial FCC structure and truncated octahedral morphology, even to room temperature under hydrogen. However, the smaller particle show a restructuration of this morphology when exposed to hydrogen at 400 degrees Celsius, leading to complete modification of its crystalline structure and stabilization of an icosahedral-like structure at 200 degrees Celsius. So to know the origin, the atomic, or to understand the atomic origin of this structural transition of the gold nanoparticle, we follow by ab initio molecular dynamic study a gold nanoparticle having the same size of 2 nanometer initially in vacuum, and then when covered by one monolayer of hydrogen between 0K and 500K. Of course, this work has been done in collaboration with our theoretical experts, Dr. Dr. King Wong, and Dr. David Lofreda. So as we see here, the molecular dynamics results show that if the gold particle keeps its FCC structure in vacuum, and even when covered by hydrogen at 0K, the morphology completely changed after 16 picoseconds of molecular dynamics to obtain a rounded morphology and to obtain a different crystalline structure. So this structural transition has been confirmed also by STEM modeling of each molecular dynamics structure obtained during the modeling. Moreover, the optimization of the structure obtained after 60 picoseconds of molecular dynamics by DFT show the formation of irregular chain, ordered chain of gold, hydrogen in the entire surface of the particle, leading to the obtention of highly disordered icosahedral-like core structure, which is completely consistent with our experimental observation. So this first study showed that during exposure to hydrogen, just the gold nanoparticle having a size less than 4 nanometer can be highly reactive and show a complete transition of the crystalline structure during hydrogen adsorption and dissociation processes. Now I will move to discuss the results of the paper published in ChemCat-Chem journal. So in this paper, we repeat the same study of the previous one, but during exposure of gold nanoparticle under static gas of butadiene. So as we see here, the small particle having a truncated octahedral morphology under argon show a change of its morphology to obtain a rounded morphology at 200 degrees Celsius, but without any transition of the crystalline structure. However, in the case of the bigger particle having a size of 5 nanometer, we have a temperature dependence of butadiene adsorption on gold nanoparticle. So as we see first at 300 degrees Celsius, the particle show a rounded morphology with different reentrant facets, a different region of the particle, which indicate that butadiene adsorption are located on 110 facets. However, when we decrease the temperature to 200 degrees C, we saw the growth of 111 and 100 facets at the expense of 110 facets, which can indicate that at this temperature, the butadiene adsorption is favored on 111 and 100 facets. So to understand the interpretation and the observation obtained experimentally, DFT-based multi-scale reconstruction study has been done on gold nanoparticle and the butadiene between room temperature at 900 degrees Celsius. So first of all, the evolution of the interface tension, of the calculated interface tension of computed 111, 110, and 100 facets at high temperature show stabilization of 111 facets and 100 facets, more than 110 facets, which can explain the truncated octahedral morphology obtained experimentally at high temperature. Then, when we decrease the temperature between 400 and 200 degrees Celsius, we saw a stabilization of 110 facets at the expansion of 100 and 111 facets, which can also explain the rounded morphology obtained at 300 degrees Celsius during ETM observation. Finally, when we decrease again the temperature between 200 degree and room temperature, we saw again a stabilization of 111 facets at the expense of the two other facets, which can finally confirm the growth of 111 facets obtained experimentally. So this DFT-based MSR study are totally consistent with our experimental observation. It's not the end of the story, because by close examination of the FFT transform, of the Fourier transform of the bright field images of gold nanoparticle, we observed the presence of diffuse streaks between the spots of the FFT patterns at 300 and 200 degrees Celsius. So based on literature, these streaks indicate the linear and planar lattice defects in the core of the nanoparticle, like, for example, dislocations, twin boundaries, stacking fault, etc. So to identify the structural defect, we applied a Bragg filter on the FFT of the image of the nanoparticle obtained at 300 degrees Celsius. And as you see here, we identified two edge dislocation at two different regions of the particle due to the insertion of a half plane above the 111 plane. Of course, this edge dislocation evolved into two entrancing stacking faults. After 15 minutes of monitoring at 200 degrees Celsius, and we saw after 63 minutes that the stacking faults is always here. So we can say that even if the adsorption of butadiene cannot induce a complete structural transition of the particle, but it can highly affect the surface structuration. Finally, by monitoring the particle oxide interface during exposure to butadiene, we saw a continuous variation of the extension of the gold TiO₂ interface between 300 and 200 degrees Celsius, which indicate a wetting and dewetting of the gold nanoparticle under butadiene. So this phenomena can also indicate that the adsorption of butadiene can be located also on low coordination sites of the gold nanoparticle located at the interface between the gold particle and the TiO₂ support. Finally, in conclusion, by grouping the experimental ETM observation and theoretical calculation DFT-based MCR model, we saw that the gold nanoparticle have a high temperature dependence concerning the active sites to butadiene adsorption, and in our region of interest, defined, of course, by the laboratory catalytic test, so around 200 degrees C, the active sites could be located at the nanoparticle surface, like 110 and 111 facets, but also at the interface between the gold particle and the TiO₂ support. Finally, I would like to thank all the researchers who contribute to obtain this original work. Of course, I would like also to thank ANR, l'Agence Nationale de Recherche en France, to funding this project. And I would like to thank also Prototypes to giving us this opportunity today to present this work. Thank you.